Okay, since it's 3 o'clock, let me start. I'll first review a bit of Galva Theory, then also a bit of Kuma Theory and Artin-Schreier Theory. All these three are purely algebraic theories. Then I'll recall what we did. About the Hilbert symbol. And then I'll sort of explain what one should be doing next. So the Hilbert symbol was just the case n equal to 2 because it's the quadratic Hilbert symbol, right? So it's a very special case of what we would like to be able to do in general. And the purpose of today's lecture is to explain what we would like to do. Okay. So let's start with the field K.
Excuse me, sir.
And so I was told that not everybody has had a course in Galva Theory. Now what we are going to review actually covered a one semester long course. So necessarily I'll be very quick and very brief. But I'll touch upon some of the essential ideas that are involved. Okay. So an extension of K is a field E together with an embedding of K.
Excuse me, sir.
So it's a pair actually consisting of a field E and an embedding of K in E. So if you have an extension E of a vector field K, then E can be viewed as a vector space over K, of course. And as such, it will have some dimension. And that dimension is called the degree of E over K, and it's denoted by this symbol. The degree of E over K is just the dimension of E as a vector space over the field K. Okay. And for the time being, I'll assume that the degree is finite. In which case the extension is said to be finite extension. Or extension of finite degree would be more appropriate. Okay. So your field K is sort of fixed. It's the base field. And you're considering various extensions of this field. Hello, is there? Oh, I see there's an echo. Somebody says. Is it still there? The echo?
Yes, sir. Yes, sir.
Is it still there, the echo? Okay, so I should mute all. Mute, right. Is the echo still there now? I hope it's not there anymore. Okay.
No, it is fine.
No.
So we have a field K, which is sort of the base field, which is fixed throughout the discussion. Then we are considering various extensions of K. We start with extensions of finite degree, okay? And they are called finite extensions. Now, whether it is finite degree or not, okay, so one of the problems would be to classify all finite extensions of a given field K. I mean, this is a very ambitious problem. You can do it only for very few fields. But as a working kind of idea as to what one would like to do, ideally, it's not a bad idea to start with this sort of problem that we have some field K which is fixed and we would like to classify all extensions of K. By the way, I'm coming to it. So for example, when K is a field R of real numbers, then there's this theorem which is sometimes called the theorem of Dalambere-Gauss, which says that the only finite extensions of this field R are R itself and the field C of complex numbers, which contains R, of course. So that's another way of saying that the field C is algebraically closed. The only finite extensions of R of the field of real numbers are the field R itself and the field C of complex numbers. So number theory is really concerned with the case K equal to Q. We would like to classify or understand all finite extensions of the field Q. And we are very far from this goal. We are very far from understanding everything about all finite extensions of Q. That will take a lot of time. But in local arithmetic, the goal is to understand finite extensions of QP. And whenever you have a global problem, like understand what happens over Q, you should always first consider the corresponding local question. So here the local question is, what are all finite extensions of QP? That's what motivates us to begin with. So we have this field QP, and we would like to understand or classify or write down, enumerate, list all finite extensions of QP. And another field which you would like to consider is this field of power series in one variable over little k, where little k itself is a finite extension of FP. So this is the case. This is also something of interest in local arithmetic, and we have done quadratic extensions of this when P is odd. Okay, but we are discussing generalities for the time being. So we would like to understand all finite extensions of K, where K is Q or QP. Now, among the finite extensions, there are these Galva extensions, which are essential, which are very important. And what is the definition? You have a finite extension E of K, and then you can form this group of all K automorphisms of E. So it consists of all automorphisms from E to E. So sigma should be an automorphism of fields, but it should take every x in K to itself. Sigma of x is equal to x for every x in K. That if this happens, we call them K automorphisms of E. So fine, this is a group. There's no surprise here, except that it turns out to be a very important group in this theory. So one can look at the fixed field of G. You have defined G to be the group of all K automorphisms of E, and then E, this is not the power, E to the G, it's called the fixed field. This is not the set of all maps from G to E. Of course, when you write A to the power B, usually it's the set of all maps from B to A, right? That's not the notation which is being used here. So E to the G is the set of all elements in E which are left fixed by every sigma in G. Sigma of x is equal to x for every sigma in G. Those x, such x, this E to the G is a field. It's an extension of K inside E, which is saying that it's a subfield of E and it contains K. So it's a field between K and E. Now, I have not defined anything yet. I've just explained that whenever you have a finite extension, you have the group of automorphisms and the fixed field of that group of automorphisms. But here is the definition. So we say that this extension E over K is Galva if the fixed field is equal to the base field, if e to the g is equal to k, right? So what you normally have, as I said here, is that k is contained in e to the g, which is contained in e. So if you have equality here, then you say that this extension is Galva. Okay. And this is what is sometimes called the fundamental theorem of Galva theory. It says that if I have a field K and E is a finite extension, which is Galva over K, then first of all, this group of automorphisms is denoted Gal E over K and called the Galva group of E over K. That's just another name for the group of automorphisms when the extension happens to be Galva, okay? But the theorem says that you have this mapping from the set of all subgroups of the Galva group. This is the Galva group, right? The set of all subgroups of the Galva group to the set of all extensions of K in E. So these are extensions what? These are fields which contain K and which are contained in E. A field L which contains K and is contained in E is an intermediate extension. Anyway, so there are these two sets, the set of all subgroups of the Galva group and the set of all intermediate extensions. And here's a map from subgroups to these intermediate extensions. It takes H, a subgroup H, to the set of fixed elements under H, the fixed field of H. It's going to be a field like this, between containing K and containing E. Similarly, if you are given a fixed intermediate field, then one can check that E over L is going to be Galva. So the diagram, maybe I should draw it here. You have your E here, L and K. Suppose you have something in between, an intermediate extension L, then one can check that E over K is Galva. That's given to us. One can check that E over L is also Galva. And so the Galva group, of course, is going to be a subgroup of the Galva group of E over L. So this map sends L to this Galva group of E over L. So now I've given you two sets, this set, and two maps, this map and this map. And the theorem says that these maps are both bijections which are reciprocal to each other. They are reciprocal bijections. Now, why is this a useful thing? It's useful because when I have this extension E over K, I have no idea what intermediate extensions there are, if any. But once I know the Galva group, and in any case, the problem has been reduced to finding out what the Galva group is and finding out what its subgroups are. And that's an easier problem than that of finding what the intermediate extensions are. So this correspondence is called the Galva correspondence, and it has some properties. One of the basic properties is that this subgroup H is normal in G if and only if this field, the fixed field EH, is actually Galva over K, right? And as a result of this, what happens is sigma of e to the h is going to be equal to e to the h for every sigma in the Galva group. Whenever e to the h is Galva over k, you'll have this property, and therefore you'll have a map from the Galva group of E over K to the Galva group of EH over K. And the property that I'm enunciating here is that this map has kernel equal to the subgroup H. Okay? So that's a very basic, the most basic theorem in Galva theory. And I just recalled it because some of you might not have taken a course in this thing yet. So more generally, an algebraic extension of a field, now you take an arbitrary extension E of the field K. I'm not assuming that it is of finite degree. I'll call it algebraic if when I adjoin a single element and consider this Kx, so E is here, Kx is going to be here, and K is here. K is contained in Kx, which is contained in E, because X is an element of E. Now, I'll call E over K an algebraic extension if the degree of Kx over K is finite for every K, every X in E. You must have, some of you might have come across a different definition where you say that it's algebraic if every element satisfies a polynomial equation with coefficients in K. You can check that what I'm saying is strictly equivalent to that other definition that you might have come across. So finite extensions, of course, are algebraic, but you might have extensions which are not finite and which are still algebraic. So for finite extensions, I've defined the notion of being Galva. Let me do it for algebraic extensions. When is an algebraic extension E of my field K going to be called Galva? Well, it's going to be called Galva if it is the union of finite Galva extensions of K contained in E. So E is here, and it might contain some Galva extensions in the sense of, finite extensions. I've defined what it means for them to be Galva. So if E is the union of all finite Galva extensions of K in E, then I say that E itself is Galva over K. So here is another way of, somewhat more symbolic way of saying it, that E is the union of all L, where L is, of course, a field containing K and containing E, and the degree of L over K is finite, and L over K should be Galva. So some algebraic extensions are Galva, some are not. Just as some finite extensions are Galva and some are not. Maybe one should give some examples of extensions which are not Galva. For example, if you adjoin a Q root of 2, then it's over Q. So K is Q and E is this. Here, the extension is of finite degree. The degree is actually equal to 3, but it's not Galva. Okay? One can actually check that this, anyway, so I'll leave it to you to check whether it's Galva or not. Okay. Now, again, so I want to define the Galva group in this case when the extension is possibly of infinite degree. It's algebraic, of course, and Galva, but possibly of infinite degree. Then what is to be meant by the Galva group of E over K? So I take any extension E over K, which is Galva, and I just, the Galva group is just the group of K automorphisms of E, right? So these are all automorphisms of the field E, which leave every element of the field K fixed pointwise. So that just means that sigma is an automorphism of E, and sigma x is equal to x for all x in K. Okay? Now, it can be checked that this Galva group is actually the inverse limit of these finite Galva groups, where what does L run through? It's an inverse system where L runs through these extensions of K inside E, so these intermediate extensions of finite degree over K, and which are Galva over K. So what is clear, I mean, by definition, E is the union of all such L's. And I'd also said that if I had L2, which is bigger than L1, which contains K and which is everything is contained in E, this is Galva and this is Galva, then I had said that the Galva group of L2 over K has the Galva group of L1 over K as a quotient, right? And these are the maps in this inverse system. It's explained here. Yeah, so if I've, instead of calling them L1 and L2, I've called them L and M. So you have the Galva group of L over K, the Galva group of M over K. Of course, it's being assumed that L and M are both Galva over K. Then the Galva group of L over K is a quotient of the Galva group of M over K. And the kernel is the Galva group of M over L. So now all these groups are finite groups because L over K is a finite extension. I should have mentioned that when L over K is a finite Galva extension, then the order of the Galva group of L over K is, sorry, the order of this is actually equal to the degree of L over K. Okay, so these are all finite groups here, and I'm taking the inverse limit of a system of finite groups. So the inverse limit is called a profinite group. So in any case, it's a topological group. That is, and the topology is important. When it's a finite group, the topology is discrete, so it's not very enlightening. Okay? And the fundamental theorem of Galva theory becomes the following in this setting of infinite Galva extensions of infinite degree. It says that closed subgroups of this Galva group correspond bijectively to extensions of K in E. And it's the same map. A closed subgroup H is being taken to the fixed field under H. So this is a bijection. That's what the Galva correspondence says. So here is an example. You see, there are very few examples where you can explicitly work out what okay, I didn't introduce the algebraic closure, but we'll come to it perhaps. Anyway, so here is an example where you take your K to be the field Fp, where P is of course a prime, and you define E by adjoining to Fp the nth roots of 1 for every n which is prime to P. So what does this symbol mean? It means some element such that zeta to the n is equal to 1 and zeta to the m is not 1 for any m, for any divisor of n. Of course, different from m itself. Strict divisor. So okay, so it's right. So another way of saying it is it's an element of order n in the multiplicative group. Okay, so here one can check that this E is a Galva extension. The Galva group is the group Z hat, which is the product of all ZLs, where L runs over all primes. And for example, Z is of course a subgroup of Z hat, but it's not a closed subgroup. In fact, Z is dense in Z hat, so Z does not correspond to an intermediate extension. It's not, there's no, it should not be. So as I said, there's a bijection between subgroups of the Galva group and intermediate. So here it has to be closed subgroups when the extension is of infinite degree. And Z would not be in this set of closed subgroups. Okay, so now let's look at, so you have these algebraic extensions which are possibly of infinite degree and which are Galva. It so happens that there is one which is sort of bigger, as big as any other, with these properties. So what it means is that, so there is a largest Galva extension, K tilde of K. What it means is that it contains every Galva extension of K, and it's contained, and if some other extension contains every Galva extension of K, then this K tilde is contained inside that extension. Or, I mean, you could simply say that it's a Galva extension of K, which admits an embedding from every other Galva extension. That's enough to characterize this as the largest Galva extension. So your field K is given, and there are going to be three problems which arise. So you have this largest Galva extension K tilde. So we have defined it. That does not mean that we have specified how it is obtained for a specific K. For K equal to R, for example, it's very easy to specify it. It's obtained from R by adjoining just a square root of -1. But for other extensions, for K equal to Fp also, this K tilde is obtained from Fp by adjoining an nth root of 1 for every n which is prime to P. So in these two cases, one can give an explicit description. The problem is to give such a system of generators for an arbitrary field, K. I don't think you can do it in general, but you should be able to do it for arithmetically interesting fields, or at least that's what the quest is, that's what the aim is. Then we would like to identify what the Galva group is. And finally, determine what the action of this Galva group on S is. So what does that mean? So for every sigma in the Galva group and every little s in this capital S, what is sigma of S in K tilde? What is this element? Okay, so here's a very baby example. Just to show that it can be done in this very particular case. So from this point of view, R is a very simple field from the arithmetic point of view, because K tilde is obtained, as I just now said, obtained by just adjoining a square root of -1. And the Galva group GK is this Galva group, right? Consists of just plus -1. And how does, so of course, one doesn't have to say what the action of 1 is, because 1 is the identity. It leaves every element where it was. What is the action of -1 is more interesting. So -1 just sends the square root of -1 to minus of the square root of -1. Okay, this is a very simple example, but here is something which is slightly more interesting. When you take your field K to be Fp, where P is some prime, then all this requires proof. It's not as if this is obvious. In this case, I mean, the proof is that C is algebraically closed. So that's not an obvious fact either. No, it requires it. But here it's even less obvious that you obtained the maximal Galva extension of Fp by just adjoining the nth roots of 1 for every n which is prime to P. And as I said earlier, the Galva group is Z hat, and just as Z is generated by the number 1, right? Z hat is also generated by 1 as a topological group. Well, that's the same as saying that Z is closed. Not closed. I want to say the closure of Z, the closure of Z in Z hat is Z hat. Z is dense. Okay, so that was the word I was looking for. One should say this is expressed by saying that Z, yeah, what I didn't know is correct, but Z is dense in Z hat. So you just need to specify what the action of this generator 1 is. Okay, and that takes your nth root of 1 to the pth power of that nth root itself. So this P is to be compared with this P. They are the same P. Okay. So in these two examples, R and this Fp, we have been able to specify what the maximal Galva extension is, what the Galva group is, and how the Galva group acts on a system of generators for this maximal Galva extension. In general, you're not able to do it. So you simplify the problem. If you're not able to do it in general, you restrict yourself to the abelian case. So what that means is that, here's a definition. So a Galva extension is called abelian if this Galva group is commutative, okay? And just as there was some sort of a largest Galva extension, there is some sort of a largest abelian extension, and it's called the maximal abelian extension of K, and denoted K ab. So given any field K, you have the maximal abelian extension of K. So actually, even at this point, you will have these three problems. So the first one would be specify a subset, explicit subset S of this K abelian such that this Ks is K abelian. That is to say, you have to specify some generators for this extension. Then determine the Galva group of this K abelian over K. And the third thing would be determine the action of this Galva group on S. So again, even this simpler problem where you are just looking at abelian extensions is sometimes too difficult to solve for the fields which are of interest to us. So one can simplify the problem further or look at a special case. So a commutative group is said to have exponent dividing n. N is some integer, right? If the nth power of every element in that group is equal to 1. Okay? So now we are given a field K and an integer n. And then there's this largest abelian extension of K of exponent dividing n. So, of course, K ab, so this is the notation, and K ab is in some sense the union of all these K ab n. Okay, so these are smaller extensions, and we would like to understand at least these ones. So this is the notation, K ab n is the maximal abelian extension of K of exponent dividing n. And we ask these three questions about this smaller extension. Can we specify some generators for the maximal abelian extension of exponent dividing n? Can we compute the Galva group? And can we determine the action of the Galva group on those generators? So the same three questions arise in this situation. Okay, so there are answers to this. There are two answers, I mean, two partial answers. So the catchword is Kumar and the other one is Artin Schreier. So I'm going to explain these things now. What is Kumar and what is the Kumar case? And what is the Artin Schreier thing? Okay, so are there any questions? So we come to Kuma theory. Here you have a field K and an integer n, and the hypothesis is that K star, the multiplicative group, has an element of order n. Such an element is called a primitive nth root of unity. So as I said, these are all partial answers. I mean, there's no answer in complete generality. So what you are given is a field K, n integer n. Partial means in some cases, some cases. And the first case is when the Kuma hypothesis is satisfied, which is what? It says that K has an element of order n, or a primitive nth root of unity. And in this case, here is what the theorem is. You denote by K star n to be the set of all elements of order dividing n. So it's a subgroup. It's a subgroup of K star sort of killed by n. It's a subgroup killed by n. So this theorem, which is the main theorem of Kuma theory, says that suppose you have a field which contains a primitive nth root of unity, then it specifies this system of generators for the maximal abelian extension of exponent dividing n. It says that the maximal abelian extension of exponent dividing n is obtained from K by adjoining the nth root of x for every x in K star. For every x in K star, you adjoin its nth root to K, you are going to get an extension which is abelian of exponent dividing n, and it is maximal for that property in the sense that every other abelian extension of K of exponent dividing n is going to be contained in this extension. So that is the first assertion of this main theorem of Kuma theory. And the second assertion computes the Galva group. What is the Galva group of this of the maximal abelian extension of exponent n? It says that this can be identified with the group of all homomorphisms from K star modulo nth powers to this group of nth roots in K, nth roots of unity in K. Okay, so this is a purely algebraic theorem. I mean, it applies to, for example, you can apply it to K equal to Q and N equal to 2, because Q contains, plus minus 1, or contains minus 1, which is a primitive second root of unity, right? So it would say that Q abelian n is 2. Abelian 2 is equal to Q root x for every x in Q. And the Galva group of this Q abelian 2 over Q is just the group of all homomorphisms from Q star modulo squares into Z star. Okay? So that is what this theorem, Kuma theory, says. Now, this Kuma theory can never, suppose I had an arbitrary field K and an integer n. Suppose n is prime, n is equal to some prime p, and the characteristic of K is also equal to p. This can never satisfy the Kuma hypothesis. Why not? Because a field of characteristic P can never contain a primitive pth root of unity, right? If zeta to the power p is equal to 1, I can write it as zeta to the power p minus 1 to the power p is equal to 0. So I can write it as zeta minus 1 to the power p equals 0, which implies that zeta minus 1 is 0 and zeta is equal to 1. But 1 doesn't have order p, it is order 1 in the multiplicative group, right? So a field of characteristic p cannot have a primitive pth root of unity. So what if you want to determine the maximal abelian extension of exponent p of a field of characteristic p? The answer is, then there's a different theory called Artin-Schreier theory, which does precisely this. Okay, so there's Kuma theory, which determines the maximal abelian extension of k of exponent dividing n if k contains a primitive nth root of unity. But if k has characteristic p, it can never contain a primitive pth root of unity. So how about the primitive, how about the maximal abelian extension of exponent p of a field of characteristic p? And that's what Kuma theory does. So here is what the situation is. Your field k has characteristic p, and we are interested in the maximal abelian extension of exponent p. So what happens when your characteristic is p is that you have this funny endomorphism. This is an endomorphism. Well, it's written here. Certainly, endomorphism of the additive group. This is p, this funny p, like this, right? It takes x to the power p. This is the characteristic. This is the usual p. It takes x to the power p minus x. And that's an endomorphism because of this fact that in characteristic p, x plus y whole raised to the power p is actually equal to x to the p plus y to the p. Okay. So because you have this endomorphism p and k is being thought of as the additive group, you have this is the co-kernel, right? This is sometimes called the co-kernel of p. What's the co-kernel of a map? If you have a linear map, U from E to F, vector spaces, linear map, then the co-kernel of U is F divided by the image of U, right? So here's the image of P, and so this is your F here. So you have this co-kernel of P of this Artin-Schreier map, and you might want to find out what this co-kernel is when your field K is FP or a finite extension of FP. Okay. In any case, you have it for an arbitrary field K of characteristic P. And what Artin-Schreier theory does is it says that the maximal abelian extension of exponent P of this field K of characteristic P is obtained from K by adjoining P inverse A. So what is P inverse A? P inverse A is any element X such that P of X is equal to A. Just as root n of A is any element X such that A, any element X, right? So it should be X to the power n such that x to the n is equal to a, right? So that's the notation. So what this theorem is saying is that if you have a field of characteristic P, and if you're interested in its maximal abelian extension of exponent P, then you just need to adjoin P inverse A for every A in K. And the Galva group of this maximal abelian extension of exponent P over K is going to be just the group of all homomorphisms from this co-kernel to FP, right? The analog earlier in the Kuma case was the Galva group of the maximal abelian extension of exponent n was the group of all homomorphisms from K star modulo nth powers and with values in the group of elements killed by n. So this is a group, this is cyclic of order n by hypothesis, and this is cyclic of order p, right? Okay. So that is Artin-Shire theory, and of course I'm not giving any proofs, and I hope that they'll be done in your courses in Galva theory. Okay, let us finally come to the fields which are of interest to us. For the time being, the fields of interest are QP and K power series T. Actually, finite extensions of these fields will also be of interest, but we'll come to them later. Right now, we have just introduced these fields QP and K power series T, where K itself is a finite extension of FP, right? And the number of elements in this little k is going to be denoted by Q. So for which n do these fields satisfy the Kuma hypothesis? In other words, for which n do these fields contain a primitive nth root of unity? They all contain QP contains a primitive nth, primitive second root of unity. That's just -1. And so does KT, except when P is equal to 2. Because in characteristic 2, -1 is equal to 1. And we have seen in general, in characteristic P, the only pth root of unity is 1. In particular, there cannot be no primitive pth root of unity in a field of characteristic P. So another n for which this QP satisfies the Kuma hypothesis, for which QP contains a primitive nth root of unity, is P-1, right? We had seen that these are the roots of T to the P-1 minus 1, and they form a set which was sometimes denoted by R star, and it's of order P-1. So that we had shown this, but here this is completely clear that this field KT contains an element of order Q-1, because this little k star is contained in KT star, and this says this is cyclic of order Q-1, right? So these are the 4 cases where the Kuma hypothesis holds. 4 pairs K, N, K being a field of interest to us, so it's either QP or K power series T, and N being an integer such that K contains a primitive nth root of unity. Okay, so what the Hilbert symbol did it worked for this pair Kn, where it was either Qp2, P is an arbitrary prime, or Kt2, where P is a prime different from 2, right? And what did it do, this Hilbert symbol? I'm now restating in different words what we had proved in earlier lectures. This Hilbert symbol established a bijection. It established this bijection between K star modulo squares and this group. This group, why is it of interest to us? Because in Kuma theory, this is the group which turns out to be, this is Artin-Schreier theory. Where is Kuma theory? Kuma theory, yeah. This is the group which turns out to be the Galva group of the maximal abelian extension of exponent dividing n. So here n is 2. So and therefore this is the group which we would like to determine. What is the Galva group? And this isomorphism answers that question. It says that, oh, the Galva group is just canonically isomorphic to K star modulo squares. Okay? Canonically, in the sense that there's a unique isomorphism which satisfies some norm condition. I don't know whether I have. Okay, so here, let me recall what that norm condition is. So I'm saying there's a unique isomorphism from K star modulo K star squares to Hom K star Z star. So this, by Kuma theory, this is the same as the Galva group of M over K, and M is K adjoin the square roots of everything in K star. This is a Galva extension of K. So there's a unique isomorphism here, such that, so let's call it rho, such that for every intermediate extension E, so E, if E is some extension here, then what can I do? You have a map from the Galva group of M over K to the Galva group of E over K. And then you have this rho, which will take you from K star, okay, first to K star modulo squares, and then this rho, right? Rho, such that the kernel of this composite map is equal to the image of the norms from E. So there's a unique isomorphism satisfying this property. This is what we have proved in the previous lectures. For what happened? There's some. Hello, can you still hear me? Hello?
Yes, sir, you're audible.
There seems to be some problem with the internet. So let's just wait for a few minutes till this gets resolved. Okay, right. So the assertion is that there's a unique isomorphism, rho, satisfying this property about the norms, right? This is what we have done. Now there's this. Now I'm going to explain what we would like to do in future lectures. So another case where the Kuma theory applies is when K is QP and N is P minus 1, or when K is K power series T and N is Q minus 1. Okay. So in this case, we will construct what is called the tame symbol. So that's going to be a map from K star times K star into FP star or K star, depending upon whether we are in this case or in this case. So we'll take A comma B to gamma AB bar. Gamma AB is this expression which we have already come across when defining the Hilbert symbol. And here, this is called the tame symbol. This here is called the tame symbol. This map. And we'll see that it actually induces a map from K star modulo nth powers to K star modulo nth powers, and with values in these things. And so it gives you a map from K star modulo nth powers. So this map is rho into homomorphisms like this. And the theorem, which is the analog of what we have done for n equal to 2, the analog of where is the theorem for, yeah, I didn't write it as a theorem, but this was the theorem here. And for the tame symbol, so the tame symbol, the theorem is going to say, and we'll come to it much later maybe, it will say that there's a unique isomorphism. This rho is the unique isomorphism satisfying this property. Now, this property can be written out like this, and it's exactly what we were saying about intermediate extensions and norms from these intermediate extensions. Okay, so what this says is that, so M is here K abelian N, N is either P minus 1 or Q minus 1 if K is equal to QP, or it's Q minus 1 if K is equal to K power series T, and of course the number of elements in this K is Q. Okay, so M is this, and this here, rho is a map from K star modulo nth powers to this Galva group. It's actually an isomorphism with the property that for every intermediate extension L between K and M, when I look at this composite from K star to the Galva group of L over K, the kernel of this composite is exactly the subgroup of norms from L over K. Okay, so now, so that was the other case of Kuma theory. And now this is an instance of Artin-Schreier theory. So here K is this. For Artin-Schreier theory, you need a field of characteristic P, right? So it doesn't apply to QP. It should be of prime characteristic. And the characteristic of QP is not P, it's 0. The residue field FP has characteristic P, not QP itself. So if I take K to be this little k par series T and take N to be the prime number P, then I'm in the Artin-Schreier situation. And the theorem there is going to be that there's a unique isomorphism from K star modulo pth powers to this so this was, remember, it was the Galva group of K abelian P over K by Artin-Schreier theory. So the theorem here says that there's unique isomorphism rho from here to here, such that X is the image of this the norm map, if and only if it's in the kernel of rho X. And no, it's not X which is in the, wait a moment. Yeah, so Y, wait a moment. Yes. Yeah, I think it's best to understand it this way, the way I've explained it here. So it says that the kernel of the map from K star to the Galva group of M over K to the Galva group of L over K is equal to the image of the norm map from L star to K star for every intermediate field L between K and M here is the maximal abelian extension of K of exponent P. Okay? So that's what this theorem will say. It's if we'll prove it later. But this shows that the theorem involves something about K star modulo pth powers and the additive group of K modulo P of K, this Artin-Schreier P. So let's first determine these two groups. What are these groups? What do they look like? Just as for K equal to QP, we determined what QP star modulo squares looks like, right? So now let's take K to be this here, little k par series T, and what we are going to determine are these groups, K star modulo K star to the power P and K plus modulo P K plus. What are these things? Okay, so we'll just start determining them today and finish it in the next lecture on Wednesday. So recall that K is this field and you have the ring O of, integral power series, they are sometimes called. And you have this valuation Vt from K star to Z, right? And the kernel of that valuation is just O star, the units of the ring O. And of course, this valuation admits a section, and any such section gives a uniformizer. A uniformizer is just an element which is of valuation 1. For example, you could take T itself as a uniformizer, right? And if you have chosen a uniformizer, then you can write K star as the subgroup generated by T. So it's infinite cyclic and times O star, the units of this ring O. So basically K star modulo pth powers is just going to be this group of order P times the units modulo pth powers. So we are just reduced to finding out what this group is. Okay, this, what are units? What is O star modulo pth powers? Okay, so there's some further reduction. Inside of O star, we have this U1. U1 is the kernel of this map from O star to K star. That's one way of saying it. And another way of saying it is that U1 just consists of all those formal parsecs which start with the constant term is 1. These AIs are in our field, little k. So this U1 is a subgroup of O star, the group of units. And it's easily checked that O star is actually the internal direct product of little k star and U1. So basically, so what we wanted to determine is units modulo pth bars, and we are now reduced to determining little k star modulo pth bars and U1 modulo pth bars. This one is very easy because little k star is a cyclic group of order prime to p. Its order is q minus 1, which is of course prime to p because q is a power of p. So k star modulo pth powers is actually trivial. So finally, what we have to find out is what is U1 modulo pth powers. That's what we need to determine. Or basically, we have to find out what U1 is. A little more about U1. So in general, if you have any n, you have Un, which consists of, which is the kernel of the reduction modulo t to the n, and t is this ideal generated by t, by the indeterminate t. The ideal t is denoted like this, and the indeterminate t is just denoted like this. So you have Un for every n, and I want to claim that in some sense U1 is the inverse limit over R of U1 modulo U p to the R. So I need to explain what are the maps in this inverse system. And the maps come from the following inclusions. You have U1, which contains U p to the R, which contains U p to the R plus 1. So that gives you a map from U modulo U p to the R plus 1 to U1 modulo U p to the R. So that gives you an inverse system. And here are the first few terms of that inverse system. It's U1 modulo U1, U1 modulo UP, U1 modulo UP squared, and so on. And U1 is basically the inverse limit of this system. So if we want to understand what U1 is, we need to understand what U1 modulo U p to the R is. Okay, fine. So anyway, what is Un modulo Un plus 1? From Un, I have this map to K plus, which takes an element 1 plus a t to the n to a bar. This little a is, of course, an element of O, right? And a bar is its image in K. So this is a homomorphism of groups from Un to K plus. And you can check that if this A is in if A is in T, then of course this A bar is 0, and therefore this homomorphism from Un to K plus factors like this. Un modulo Un plus 1 to this. Okay. And the claim is that this mapping is an isomorphism of groups. In other words, we are saying that un modulo un plus 1 is, this mapping gives you an isomorphism of this multiplicative group with this additive group. Okay. So first of all, we have to check that it's a homomorphism. So if I take two elements, their product sort of gets converted into the sum of these two coefficients, right? And the kernel is visibly un plus 1. That's it. So you have this homomorphism from un to k plus, and which is surjective. And the kernel is un plus 1, and that's it. That proves the statement. Okay. Next, I claim that if I have an x in un, which is not in un plus 1, then its pth power will be in upn, but not in the next one, not in upn plus 1. In other words, so this will induce a map, raising to the pth power will induce a map from un modulo un plus 1 to upn modulo upn plus 1. And the claim is that this is an isomorphism of groups. And here's the proof. To say that x is in un but not in un plus 1 is the same as saying that when I write it as 1 plus a times t to the n, where a is of course in O, it's to say that it's not in the next one is the same as saying that, oh, wait a moment. It's not this tall, right? This is not what it is. So what it means, what one has to say is that A is not in T. Instead of O star, I had to write T. Yeah. And so now if I raise 1 plus a t to the pth power, then I'll get 1 plus a to the p, t to the pn. And for the same reason, I mean, if a is not in t, then a to the p is not in t either. Yeah, so here, of course, a not in t could have been written as a in O star. Okay. So if a is a unit, then so is a to the power p. And therefore, x to the p is going to be in upn, because the exponent here is pn, but it's not in the next one. So basically, we have proved that this is an isomorphism, and the same reason applies to this here. So these two vertical isomorphisms, and you have the raising to the power p map here, and raising to the power p map here as well. And this diagram, of course, commutes. But at the bottom map here is, of course, an isomorphism. It's sometimes called the absolute Frobenius or whatever. Doesn't matter. But when you have a finite extension K of Fp, the map x goes to x to the p is an automorphism of the field K, right? Actually, it's the Galva group of K over Fp is, so if I call it sigma, then it's generated by this sigma. Anyway, so the bottom arrow is an isomorphism, and so therefore is the top arrow. So that proves this statement. And now I claim that un modulo upn has exponent p and order q to the pn minus n. Why is that? So whenever I have an x in un, x to the p is in u pn. That's what I've proved. So this group has exponent p, because, okay, I mean, exponent dividing p, but then I could say that 1 plus t, for example, has order p. The image of 1 plus t in u, 1 plus t to the n, I should take, in un modulo u pn. This is an element here which has order p, and therefore the exponent of this group is exactly p. In other words, this group is not trivial. Okay, so we know its exponent now, and we have to show that its order is equal to this much. In order to compute its order, the order of this group, I've written a sequence of subgroups. So this is un modulo upn. It contains un plus 1 modulo upn, which contains all the way down up to upn minus 2 upon upn, and upn minus 1 upon upn. And finally, this is, of course, upn modulo upn. Now, there are these p minus 1 successive quotients here, 1, 2, etc., all the way up to here. And each of these, the successive quotients here are actually just ui modulo ui plus 1, which we have seen is isomorphic to k plus. And this is some isomorphism theorem, right? In group theory, whenever you have, so this is something that you should be able to recall from your courses in group theory, right? Now, each of these successive quotients has order q. So the order of un modulo upn is this here. Q multiplied by itself this many times, because there are that many terms in this filtration. So I've determined this, and similarly, so what I had proved was about un modulo upn. Now I'm proving something about u1 modulo up to the r. It's not p times r, it's p to the exponent r. So this group has exponent p to the r and order this much. So the same reasoning, I mean, you do something similar. We have seen that x to the p to the r will belong to this u p to the r for every x in u1. And therefore, the exponent of this divides p to the r. But to say that it's exactly equal to p to the r, you have to produce some element which has order p to the r. And here is an element, 1 plus t. So the exponent is exactly equal to p to the r. Sorry. Okay. And the order, okay, so the order is, you do as induction on R. You first compute the order of U1 modulo UP, then you compute the order of U1 modulo UP squared using this knowledge and so on. Okay. So our U1 was this inverse limit, and here it is spelled out. Now we have proved that this one, of course, is a Z mod P module, which just means that it's a commutative group of exponent P. We have proved that this one is a Z mod P squared Z module. In other words, we have shown that this is a commutative group of exponent P squared. Similarly, we have proved that this is a commutative group of exponent P cubed. So it's a Z mod P cubed module. And Z mod P squared, Z mod P cubed, they are all ZP modules, right? Z, or they're quotients of ZP. So each term in this inverse system, each term can be viewed as a ZP module. So the inverse limit is going to be a ZP module. Okay, so this is something very funny going on here. You have an X which is a formal power series with the constant term 1, then x1t, x2t squared, where the xi's are in this finite field K of characteristic P. And you have this A, which is in ZP, right? A is in ZP. So you can write A as A0 plus A1P plus A2P squared, where these AI's are in the interval 0P, 0 to P minus 1. And then we are saying that this x to the power A makes sense for x, this infinite power series, and for A, this infinite power series in P, where x has this indeterminate T. Okay. So, in other words, U1 is a ZP module. And I don't know how much I have, but maybe I have enough time to finish what I want to say today. Maybe I'll also take it up again tomorrow. But so now we have made this U1 into a ZP module. And the claim is that it's not finitely generated. Okay. So how do I show that it's not finitely generated? So it's enough to prove that this index is not finite, because if it's finitely generated, of course, this index would be easily calculated. I mean, you can easily see that this index is also going to be finite. Okay. So this is what we are going to prove, that the index is not finite. And we know un to the power p is contained in unp. And so this is the inclusion I have written, and unp is of course contained in un. So this index of this last one in the first one, right? This index is certainly going to be bigger than this index. That's what I've written. And this index we have computed. It's equal to this. So keep this in mind, that the index of un to the power p inside un is bigger than this. Okay, now we also have these inclusions. U1 contains un, so you have these inclusions, and of course these inclusions. So remember, you notice that the first and the last terms are really the same in these two inclusions. So I can compute the index of un to the power p inside u1 in two different ways. I can compute this index in two different ways. Here they are. The first way is using the fact that the intermediate thing is un. So it's going to be the index of un in u1 times the index of un to the p in un. And the second way is that it's going to be the index of u1 to the power p in u1 times the index of un to the power p in u1 to the power p. But these two things are really the same, because there's no p torsion in u1. So I can cancel them out. And what I'll get is that this u1, this index of u1 to the power p in u1 is the same as the index of un to the power p in un. But this we had seen is greater than q to the pn minus n. But this n can be chosen to be arbitrary, as large as I wish. But this is a fixed index. If it is finite, it cannot be bigger than every power of q. So we have arrived at this absurdity by assuming that this index is finite, So the only conclusion, the only escape is to conclude that this index is not finite. And that's it. So that's what, the time is also up. So we will take it up on Wednesday. And on Wednesday, we'll also determine K plus modulo P K plus, when K is equal to this little k bar series T. Right. Are there any questions? No? Okay, if not, I'll stop this.